All right, I'm going to talk about some work in progress. It's okay. So I'll start by giving a very rapid recap of the framework that I'm working with, because as we know, there are a number of different frameworks that people use, and maybe this is helpful just so that we don't trip over terminology and so on. I'm going to spend a great amount of time on this. If someone wants to jump in with a question, do, but I don't intend to spend a long time on this. So we could take as a starting point the idea that anytime we interact with physical systems, it gives rise to empirical data. And this empirical data is something that we can study and analyze. So we might tabulate the data in one of these probability tables, like we have here on the bottom right, where we have inputs and outputs and probabilities for a given output, supposing that we've put in a given input. In terms of how we actually treat this, how we formalize it, so I'm working with the Abramsky-Brandenberger approach to formalizing empirical data. And so the first step there is to formalize the kind of experiment that's being described. And so that can be formalized as a measurement scenario, which has three components. First, a finite set of measurements. Second, some compatibility structure on those measurements, telling you which measurements can be jointly measured. So mathematically, that has the structure of an abstract simplicial complex. That is to say, if I can jointly measure some subset of measurements, I can also jointly measure any subset of those. And the third component is that we need to specify some outcomes, the possible outcomes for each of the measurements. So a measurement scenario is how we formalize the type of experiment that we're doing. So if you like, that's kind of like an empty probability table. It's telling you the shape of the table, but it's not telling you the data that's in it. Some of you may also have seen bundle diagrams before. Essentially, it's like a bundle diagram without putting the information upstairs of what the probabilities are and what the events that can arise are. So we'd like to fill those in. And so the next thing is that we formalize the data itself that goes into the table as an empirical model. And so that is a family of probability distributions where there is one probability distribution over the joint outcomes for each context of measurements. Something that we would usually assume with empirical models is that marginals are well defined. So that if I have two different contexts that overlap on a particular measurement, I can obtain a probability by marginalizing from the first context or from the second context, and these marginalized probability distributions should agree with each other. So that's something that we would usually assume. That's what I'm going to call the generalized no signaling property. So when we're talking about Bell type scenarios, this is on the nose, what you know as no signaling. It's also something that holds for quantum mechanical models where we're not necessarily supposing Bell scenarios, but where we're just talking about measurement compatibilities, perhaps on a single system. Okay, so moving forwards, then we can talk about non-contextuality of an empirical model. So when we make an assumption of non-contextuality, the assumption that we're putting in is that the system in question, it has some sort of global value assignments under the hood somewhere. Maybe we don't have access to them, but as we measure, the idea is that we should be revealing these values. Of course, we might only have probabilistic information about what that global value assignment is. And so non-contextuality allows that we have mixtures of those assignments. And we say that an empirical model is non-contextual if and only if it arises from a distribution on these global assignments. So there it is written in slightly more mathematical language. So you have a distribution on global assignments such that for each context, when you restrict by marginalization, you get just the empirical probabilities. Okay, so that's talking about non-contextuality. I want to mention a measure of contextuality. So this is something that we explored in quite a bit of detail in a paper with Samson and Rui from a few years ago. So we use linear programming to optimize the fraction of the data that can be simulated classically, that can be modeled with global value assignments. So in a sense, we're not in a sense, precisely what we're doing is we're trying to decompose the empirical model into a non-contextual part, which arises as a convex combination of global value assignments, and something that's left over. The thing that's left over turns out to be what we call strongly contextual. It's an interesting story in itself, but this is how we set it up. So we try to optimize. We come up with, we use linear programming to get an optimum sort of decomposition where we've given maximum weight to this non-contextual part. Okay, something that's nice about this measure is that it corresponds to a normalized violation of an optimal Bell inequality. So if you were to run the dual program, the dual linear program would actually calculate a Bell inequality that's optimized for the data. So in a sense then, the contextual refraction, it generalizes the approach that we usually think of in terms of Bell inequalities, where there is a given Bell inequality and we want to know if the data violates it. Now we just take the data and we have this method which actually finds the optimized Bell inequality, or finds a violation with respect to an optimized Bell inequality. So then we get this inequality for witnessing contextuality, which is that the contextual fraction should be greater than 0. So I call this like a master inequality. Somehow it sort of contains all the Bell inequalities within it, if you like. Okay, there's another way of talking about things, which is in terms of hidden variable models. And so that's something I want to touch on briefly now. So with hidden variable models, we're going to postulate some set of hidden variables. These might be the underlying physical states of a system if we were looking for a deeper theory than quantum theory, for example. Each hidden variable, it should determine empirical behavior. So for each lambda in this set of hidden variables, we actually have an empirical model. So maybe I should have put that in quotes because, you know, empirical meaning what we've actually observed. Okay, maybe we don't observe the this precise behavior because we've got a distribution over the hidden variables, but the mathematical object is what we've defined as an empirical model. Okay, so maybe we only have probabilistic knowledge of it. Then we would say that an empirical model is realized by a hidden variable model if, given the probability distribution and summing, you know, over the weights assigned to the different hidden variable empirical models, we recover precisely the empirical model that we were interested in. Okay, so with hidden variable models, we're taking the empirical data, we're trying to explain it by another distribution over these hidden variables, hidden variable behaviors. And the hope is that these H's, the hidden variable behaviors, might have nicer properties. So we could be looking for things like determinism or various kinds of independence, locality, for example. Okay. All right, so when we're in hidden variable language, non-contextuality, it can be boiled down to two assumptions. And typically, I think that's how people would talk about it. So it's two assumptions on the hidden variables, that the hidden variables should be deterministic, which is to say that whatever hidden variable you have, whatever context you're in, there's going to be one outcome that results with certainty. And the second thing is parameter independence. And parameter independence says that for each hidden variable, the behavior we're looking at is generalized non-signaling itself. So fixing any lambda, we still have well-definedness of marginals when we look at the behavior. Okay, so an empirical model we say is non-contextual if it can be realized by a non-contextual hidden variable model in hidden variable language. This actually matches the definition from earlier. So that's a central result in the original paper from Abramsky and Brandenberger. There is a way of seeing this, which is relatively straightforward, but in the interest of getting to some of the more interesting things I want to say, I'm going to skip forward. So something that many people have done, something that is wide open for discussion, is to question the validity of the assumptions that go into this. So remember now that we have two assumptions, determinism and parameter independence. So determinism, first of all, we could argue that it's valid only to the extent that the measurements we're making are empirically sharp. Now, there are a few different approaches to saying what sharpness means. I'm going to go with this one, which is to say that a measurement is sharp if, upon repeating it, we would always obtain the same outcome. Now, the objection here is that the measurement device itself could have some sort of indeterminism in it. So if I'm feeding it the same state all the time, maybe there's still some indeterminism in the measurement device that's giving me, probabilities of various outcomes. So if it were sharp, given the same state, given the same states that we're not being invasive and changing the state, we expect that we see the same outcome every time. So this is something that we could actually go out and measure. So determinism is one assumption that we could attack and say that, okay, maybe it's only valid to the extent that really the experimental measurements are sharp. The second one is parameter independence. And here again, we might say that, well, this should only really be valid to the extent that the empirical model I'm looking at is no signaling or non-disturbing or generalized non-signaling, whatever you want to call it, in the first place. And so that's something that I'll come back to. I'll mention a few situations where this no signaling certainly does not hold. Okay, so first I want to talk about unsharpness. And so I'm going to analyze unsharpness on its own, first of all. From the outset, let me just be clear that what I'm doing, I'm essentially following the approach of Kunjwal and Speckens from these papers and Kunjwal. But I'm working in the sheaf theoretic framework. My intention is to link this analysis up with the contextual fraction. And the second difference is that I'm following the Kirabella and Yuan approach to unsharpness, which is this thing in terms of repeated measurements. As I said, there are other ways that we could talk about this, but this is the one that I'm taking, the one that I found the simplest. A point about this approach to trying to assess sharpness is that empirically it does require something different to happen in an experiment. It requires that whatever context of measurements you're performing, you don't just do it once, but you do it twice. So each context has to be performed twice in succession now. So it does actually place additional demands on someone who might be doing it in the lab, for example. So for now, I'm going to ignore the presence of signaling or disturbance and just attempt to talk about determinism in isolation. And then afterwards, we'll come back to signaling. Okay, so I'm going to quantify unsharpness with a fractional measure. And so let me talk you, this maybe looks intimidating as an expression. It's not so intimidating. So let me just talk you through it. We'll just fix ourselves on the numerator in this expression. So what I'm doing is I'm running through all maximal contexts and all outcomes that might arise in those contexts. And I'm just looking at the probability that the second measurement differed from the first. So all I'm doing is I'm summing over all of the events that might have arisen, and I'm looking at the probabilities that the second measurement differed from the first, that there was something unsharp happening. I'm summing these. If I just took the numerator, it wouldn't be normalized. I want something that's normalized. So the denominator is a worst case scenario. And so for worst case scenario, as I said, we're still going to be assuming non-signaling at this stage because we just want to treat sharpness in isolation. So I'm going to take a maximum over all non-signaling behaviors, and I'm going to see what the likelihood of, having a behavior where, the outcome can change if I repeat the observation. So we've got a worst case scenario on the bottom, and we've just run through each context and each outcome and seen how unsharp they are on the top. Okay. So one kind of fairly trivial proposition to mention from this, or that falls out from this, is that if we are perfectly empirically sharp, if this measure evaluates to 0, then if the empirical model has a parameter independence realization, then it's also going to be non-contextual. Okay, so I won't go through this in great detail, but essentially when we're sharp, you can run through the argument that given a lambda, the measurement response must be deterministic, and you kind of force determinism. So via sharpness, you force determinism onto the hidden variable model itself. Okay, moving on. So the moral of the story to this point, just when we're talking about unsharp data, is essentially that to witness what we might call genuine contextuality, that is to say, contextuality that couldn't just be attributed to, okay, well, the measurements were unsharp, it doesn't matter. It requires that the contextual fraction exceeds the unsharpness fraction of the data. So then we get this kind of new master inequality for witnessing contextuality, which is that the contextual fraction just exceeds this unsharpness fraction that we've introduced. Okay. To be a little more precise, if this inequality holds, then E, the empirical model, doesn't admit a parameter independent hidden variable model. So, to this point, we're just saying that unsharpness can be accounted for by adding a correction term to the contextual fraction, this epsilon. Okay, let me move on because there's something else I want to say very rapidly as well. So now it's signaling data. So again, from the outset here, let me explain where the motivation and inspiration comes from. So this way of approaching things is very strongly inspired by the CBD approach of Hector and others, and also by work from Andreas Winter. So I'm drawing heavily on these, again, just trying to express it in a language of the sheaf theoretic approach, and with the intention of getting a correction to the contextual fraction. Okay, about signaling, one thing that we should be clear about is that signaling, it is always going to be a feature of signaling. Here I mean generalized signaling as well. So it's always going to be a feature of experimental data. So one argument for this is that just due to finite statistics, even when the behavior is in accordance with signaling theory, you will still witness some deviation from that. There are other arguments, maybe systematic errors play a role, or there's a whole Meyer, Clifton, Kent line of thinking to go down, which I don't want to get too deep into, but which might also give some reasons to be cautious. Okay, so again, same approach, try to quantify signaling. Is a measure that I'm using because the one that's matched up easiest with what I was trying to do. Other measures are definitely possible and I'm sure will be interesting, but here just as a first attempt, I'm going to quantify the signaling of an empirical model in terms of total variation distance. So I'm taking a maximum over the total variation distance between for all pairs of contexts, for all pairs of maximal contexts, in fact, suffices. At this point, let me just make a side remark. So usually we define empirical models to be non-signaling. So it's still well defined to talk about empirical models where this marginal property doesn't hold. So that's okay. In this case, the non-contextual fraction, we try to maximize the fraction of the data that can be described by a deterministic, parameter-independent, hidden variable model, global value assignments, if you like. That's still meaningful. On the other hand, the leftover, the remainder, the contextual fraction, it might comprise some portion of data which is signaling rather than what we might call genuinely or parameter independently contextual. So that's what we need to bear in mind. Let me give just rapidly one definition. So we'll say that a hidden variable model is epsilon parameter independent. So we're relaxing the notion of parameter independence. If for each hidden variable, we have the marginal property defined again up to epsilon. So sigma is the this total variation distance measure that we were using. Okay, and so similarly, we can say that an empirical model is going to be epsilon non-signaling if this measure in terms of total variation distance is below epsilon. Okay, so the proposition is that an epsilon parameter independent hidden variable model realizes an epsilon non-signaling empirical model. So that's relatively straightforward. Just trying to manage my time now so I can say the most important things. Okay, so actually, let me just really plow through. So the main theorem that I want to say is that if the contextual fraction beats this signaling measure, then E cannot be realized by a parameter independent hidden variable model. So I could go through the proof outline here. So I'm relying on one result from Winter and one property of the contextual fraction, which is kind of a continuity property. If two models are close in the variational distance, then I can also bound the distance of the contextual fraction. So let's just leave a minute or two afterwards. I'm going to leave that alone. In conclusion, a sufficient condition for loophole-free contextuality. I put it in inverted commas because I'm talking about two loopholes, right? An objection to parameter independence being a valid assumption and to determinism being a valid assumption. There are other loopholes, of course, and there always will be with no-go theorems. One that has been very nicely studied, for example, is by Fried, who spoke earlier in this session, and collaborators in terms of measurements that are made in sequence rather than perfectly simultaneously in experiments. I'm not talking about that. Somehow that deviates from the hidden variable models framework a little. So just for the two loopholes that I'm talking about, we can close them if we have a contextual fraction that beats the sum of these correction terms. Okay, and then just so I'll wind down, but I just want to very rapidly mention. So some of you might have noticed that I changed affiliation in the title slide. So I'm now working at a photonic quantum computing startup. So I thought I would mention that too, because it's the first time I see many of you since I have moved. happy to talk to anyone about this stuff. So it's a hardware company that's developing single photon emitters. I joined to start the theory applications and software team. We're recruiting. So if you have people who are interested in jobs, foundationally minded people would be very welcome. Also open for collaborations if any of you ever see any nice things that we could maybe do together. So yeah, I'll wrap up on that and take any questions if there's any time.
Well, thank you very much, Shane. The floor is open for questions.
I would like to make a question if it's possible yet.
Yes, it is perfectly well.
Thank you. First of all, Shane, thank you very much for the very interesting talk. My question is, you said that there is an inspiration, or at least a relation with the Speckins framework for contextuality, which doesn't assume outcome determinism, right? And I know that there are some works using this approach, where you can actually also deal with the problem of not perfect equivalencies. So my question is, how do these works relate to your? Is it like a one-to-one straightforward relationship, or is it something that is not yet fully understood, the relationship of your loophole-free and their, as I think they call it, like unwarranted idealizations or something like that?
So I don't know that I can give you a very clear answer, like on, it depends at what level of generality. So in terms of what I've presented here, in terms of trying to just treat unsharpness as like an objection to the validity, of witnessing contextuality. Here, I've very directly taken inspiration from what they've done. Essentially, what I'm doing is trying to re-express the kind of arguments that you find in the papers that I mentioned earlier. I'm trying to re-express that in a language that's closer to mine. But in doing so, I've introduced, I think, a couple of differences and novelties. So the connection with the contextual fraction is something which kind of generalizes Bell inequalities, I think is a strengthening in some sense. And I've also used a description of sharpness that ultimately probably can be brought around to being equivalent to what is talked about in the Kundral and Speckins papers, for example, but which I found simpler and I think on the nose might come across clearer to the non-initiated. That's my take on it. But I mean, yeah, okay. I could maybe say other things, but we could talk further at some later point.
Sure, thank you very much.
Shane, I have maybe 30 minutes to ask my question, and it's brief. Is this last inequality a definition or a theorem that contextual fraction should exceed the sum of two measures that you have just introduced? Just the question is it a definition of a kind of genuine contextuality, or is it a theorem that's proved from some other definition?
It is a theorem, and probably now that you say it, I would have done better to express it as such. So maybe the material is a little bit undercooked, but yes, okay, thank you for the question, because it allows me to clarify that. So yes, I think we can see this as a theorem. I'll just point out one thing as I'm looking at the slide, there's an error there that should be strictly greater than, rather than greater than or equal to. But yes, so if I want to make the statement in the form of a theorem, it would be this second bullet point. So the empirical behavior E cannot be realized by as so a sigma parameter independent. So I've weakened parameter independence. It cannot be realized by a sigma parameter independent hidden variable model if this inequality holds. So then you can try to interpret this. So I would interpret this as being, I mean, maybe we can interpret this as being a witness of genuine contextuality, because it means that whatever contextuality is there cannot just be fobbed off on sharpness or signaling, or the combination of them.
I see. Thank you.